right, folks. Our special guest for tonight is Tommy Reed. He is a regular in the chat room. I think a lot of you have probably argued with him about something over the years. He's been in the chat room for, well, excuse me just a moment. Damn, that's loud. Turn that sucker down. In any case, it's always something at the Scarecrow show. You can't have a show without a glitch or two. In any case, Tommy Reed, how you doing tonight? Give me a quick sound check. Let me make sure I get good audio on you.
1, 2, 3, 4.
All right. Yeah, I got you good. Well, I'll tell you what, sir. I understand you're going to show us your prototype of the rotary piston engine. I do have a little video that you provided to me. If you'll stand by for just a second, I'm going to go ahead and play that video for the audience just to give them a little taste. And as soon as the video is finished, I'm going to transition right over to giving you full screen, and you just take it away, and we're interested in hearing your presentation. Here goes with the video.
The rotary piston engine offers a totally different, unique design, unlike the IC internal combustion engine. An internal combustion engine usually uses a piston with a crank and a piston rod. These all are basically linked together to convert this shaft into direct output of mechanical work. The rotary basically consists of just three major parts, and that's the crankshaft, which is basically a shaft, a rotor, and a piston vane. This vane travels the inside of the walls of the housing, allowing it to convert that into direct output. So when these both are running, you can see that in this particular design, we actually have a greater stroke on the rotary, but also we have less cubic inches of travel. The prototype basically consists of about 20 cubic inches of displacement. Unlike the piston engine over here, this engine is going to use much more, roughly between about 10 cubic inches on this full stroke by the time that energy comes all the way out. But the problem is that when you put these under a load, the energy still wants to expand. This is also the reason why you need a muffler. That energy is being released because it can no longer do any mechanical work. So basically you're wasting engine in the typical IC. In the rotary, we want to be able to use as much as we can, roughly 340 to 320 degrees complete power stroke. Also, we can get at TDC instant torque, unlike the typical IC engine, which you cannot convert that into any torque at all. So this is basically the concept of the rotary piston engine. Okay, on these designs right here, now I want to explain to you in details what's going on.
All right, sir. It's your presentation at this point. Take it away.
Okay, if anyone's remembered the last video I did on this small rotary piston engine, basically it was sort of like an air tool, and what I was doing is testing some of the theories behind the rotary piston engine. I got about 5 years of research on this and testing different designs. Here's another one I built just to test the rotor and how well it wears and vice versa. So what I'm going to show you now is actually a real gasoline prototype. It's about 75% completed, and I'm still working on the upper part of the design. So let me go through that real quick and move the video to show you what it looks like. And on this particular video, I can actually zoom it too if you need to see a little closer. There we go. Now, let me explain some of the details of this rotary. Actually, I ended up putting this light here just to check the color. Sorry about that. But let me explain something to you about this rotary engine. What this consists of is taking a regular standard engine and just compressing the air and fuel mixture. That's all we're using it, basically as a compressor. And what that's going to end up doing is, like an air compressor, is going to take the air and fuel mixture, compress it into a chamber, and then that chamber gets diverted over to the rotary. The rotary then will take that energy in and rotate the vane completely around about 330, 340 degrees, depending on the distance of this. But what you're actually doing you're taking the existing energy. Now, this is a typical 3.5 horsepower engine. That means that that's the most I can ever get out of this. But when we take that energy from the heat from the fuel itself, and yeah, I'm still using fuel because there's a lot of energy in gasoline. What I'm ending up doing is basically taking that energy and rotating it into a circle, which will increase the power output so dramatically. We're talking pressures as high as 2,000 psi's in the combustion chamber. Here's a unique thing about it, is that even at 2,000 psi's, we have a constant 3-inch crank. A 3-inch crank means that whatever pressure I put on this rotor, we're going to multiply that by 3, especially when I only have a cubic inch. I have 1/5 the size of this piston inside this rotor. That means that when this moves 1 inch down, this is probably roughly about 5 cubic inches of air movement on this piston. This is the maximum amount of torque this engine could actually produce at 90-degree angle. But what happens at 2,000 psi dropped down tremendously, so you actually lost a lot of energy when you have a piston in this function. But when you have a rotary at TDC, you're talking at even at 3,000 psi. Because basically what you're going to do, you have to multiply this dramatically. You're taking a roughly 2,000 psi's under a load. You're going to break it down to about 1,000 psi because it has to take up a cubic inch in the rotor. But then you're going to multiply that again by 3. You're going to get 3,000 inch-pounds on this shaft at TDC. How much is that? Look at 250 foot-pounds. That's how powerful you're looking at. So now we're taking a basic engine, the same energy, and now we're converting it into true output of work. The beauty of this is that we have a long stroke on this. As you know, a typical engine can only have the maximum stroke of 180 degrees, and that's if you can get anything out of it. By the time this gets to 180 degrees, that valve is opening to the exhaust. You ever wonder why you need a muffler? You hear this giant bang. That is the fuel to still expanding. The pressure is so high, it's like releasing pressure. In the rotary, we want to take that and use it completely all the way around. So we're taking that energy and literally converting that into direct output. Here's the interesting part about it. That means you could use less fuel to equal the same horsepower of a standard IC engine. And that's the beauty of the rotary piston engine. Now, this engine actually weighs over 100 pounds. And the reason it is so powerful or so bulky is because we're dealing with tremendous pressures in this rotary. So I need a lot of metal for that thickness to withstand the pressure. But when this actually spins over, the exhaust, because it has to travel 340 degrees, basically, the exhaust will be very low because you're using all that pressure up. You got 20 cubic inches in this full stroke compared to only 10 total cubic inches of a stroke here before it comes out of the exhaust. So basically, we're going to use whatever is being converted from heat to pressure and convert that directly into output of energy. And this is very critical because a lot of people don't understand is that today's fuels are so watered down. You know, it is said that basically a gallon of gasoline is about 125,000 BTUs. Because they put so much junk in it, you're lucky to get 100,000 BTUs per gallon. Well, the BTUs is what really runs this any engine, any IC engine. It's the heat. As Charles Laws has always quoted, anytime you have a containment and you double the temperature, you also double the pressure. So just imagine we're actually using heat to drive these engines. What I want to do is use that heat and drive the rotary, and the only way I can do that, there is no compression in this rotary whatsoever. So I have to have an outside compressor. And that's basically what it comes down to on this particular design. Can you hear me, Gary?
Oh yeah.
Okay.
Now I was going to try not to interrupt you while you're right in the middle of your
Yes.
presentation. Now, we do have quite a number of active questions.
Sure. Any questions? Look, I've been doing this for a long time. I got a tremendous background in mechanical. I worked on many engines. And an engine, there's a basic rule about an engine, and that is you have to have compression, you have to have fuel, and you have to have spark. Anything other than that, it's just basically bogus, because you still have to have those basic mechanical capabilities to convert that into work. And the unique thing about this, the reason I added this already pre-made engine, I saved a lot of money in machining, because we're looking at a total right now. I got about $2,000 in this prototype. And it sounds like a lot of money, but it could actually be even higher than that if I'm not conservative. So everything that's made is made for some serious output. You know, this is not a toy. Unlike my past test with the air, we're not using 120 psi. We're using tremendous pressure, and this has to withstand that kind of load.
Now, if I understand the concept correctly, the ignition will actually take place in the little single-cylinder motor, right?
No, it will not take place in this cylinder. That's the unique thing about this. I'll tell you what happens. When this actually pulls in the vacuum and pulls the air and fuel mixture, it comes up and compresses. Now, that energy gets diverted into an external combustion chamber. What I mean by that is that there's two check valves, like a regular air compressor. As you know, when you turn on an air compressor, the air is just being pumped in and never going back into the piston. That goes into an external combustion chamber that literally is a special design. Think of it as a self-contained combustion unit itself. Here's the beauty of this.
So
go ahead.
Basically you're using the single-cylinder engine as a compressor. You're going to compress the air and fuel into an external combustion chamber where you will ignite it, and then the expanding gases from that will be channeled into the rotary to actually give you the force to rotate not just the rotor, but also the little gasoline engine.
Yeah, because these are all connected as one. The shaft and rotor is one unit, as you can see. It's all one unit. Now, I'll tell you what's going to happen. Over here, there's a timing gear that will be here. There's an upper cam. There's a cam unit that I'm designing. It has a timing belt. What it does, this actually ignites before it even allows the gas to expand. In other words, when this compresses into a chamber, it actually ignites it and burns it. Now, this is critical because most engines, that when they ignite at TDC, they don't have time to completely burn. So the combustion chamber, internal combustion chamber, actually will burn for a period of second before it's being released into the rotary. So in other words, there's a cam that opens up the release valve and allows that energy to be diverted directly into the rotary. So it actually pre-ignites into the combustion chamber, and when that heat is heating up, it's going to expand the pressure, and when it gets to that point, it actually releases it then. In other words, it doesn't release it like a typical engine, where at TDC you're firing it and it's working against itself. I want to be able to literally burn that fuel into the combustion chamber before it actually is released.
Gotcha. Okay. But by the way, folks, Tommy has put together a website, and the URL for that website is in the lower third there. So do your Lindsey William things. Take your pencil and your piece of paper and jot down that URL. So if you can slip by there and see an explanation of just what it is we're looking at. But at this time, is it okay if we take questions, Tommy?
Absolutely. I am well versed. Let me just mention one thing.
Please.
Ideal gas law, which is PV over nRT, is very critical. That's the mathematical formula to know how many moles of gasoline it takes to actually run an engine. I have done calculations on this particular design, and it could use as high as 1/64th the amount of fuel to equal the same horsepower as this little engine.
So you're expecting
we're expecting such a huge efficiency that you could use less fuel and get the job done with greater output of torque. We're talking something that has instant torque at TDC. People have no idea that a typical engine, when that piston is being forced down by all that pressure, think of an elephant stepping on that piston. That's how much force is involved just to turn over an engine. So you have a bunch of elephants pushing down your pistons to move your car down the road. It is totally ridiculous.
All right, Dee. We addressed, I think, the one question that came up 2 or 3 times there early while Tommy was still doing his presentation. Combustion takes place in an external combustion chamber. The engine draws in the air and fuel. That is then compressed by the engine into this external combustion chamber. The fuel and air mixture is ignited in the external combustion chamber, where the expanding gases are then channeled to the rotary to provide motive force. Is that a reasonable, quick and dirty explanation, Tommy, or did I screw up?
Absolutely. Now the key is that the combustion chamber size is critical. Now, I already know the size of my combustion chamber, so I have to actually add how much energy it takes as far as displacement from getting from point A to point B. Now, the beauty of this is that I can actually run this every revolution per minute and let it fire, or I can change the direction of fire. You have to understand, we have a huge inertia going on into this engine. This rotor inside is extremely heavy. That means that once you move a inertia and you get that going, it's not going to take long to use less energy to keep this running. And the beauty of it is torque. Always remember, an engine is only an engine if you can supply the torque. We're talking at my figures a constant torque of unbelievable proportion. And the beauty of it, we could be looking at over 150 horsepower in this model.
Okay, one question that's come up here, and it's an interesting question. Why not use a two-stroke engine for your compressor?
Well, here's the problem with a two-stroke, and actually it's not a problem, but because I need a certain displacement, a two-stroke has a displacement area in the combustion chamber so small it wouldn't even do anything for this. I need volume of compression. In other words, like, no different than having a 4-inch piston. The reason there's a 4-inch piston is because it's able to compress a greater volume. The greater volume, you can fit a greater amount of air and fuel mixture. That will also give you greater output in power. So I need at least a cubic inch of area for my combustion chamber. And then I can understand that with that cubic inch, we ain't talking 120 psi. We're talking pressures that will exceed 2,000 psi. Give you an idea. When this thing is actually charged, pre-charged, at a cubic inch of area on a combustion chamber, this shaft is going to move about 18 degrees to use up a cubic inch. That means that the 2,000 psi actually dropped down to 1,000 psi because of that 1 inch of movement in displacement. But it's actually 3,000 inch-pounds on the shaft because you have a constant of a 3-inch crank. Where in the heck have you seen a 3-inch crank lately? Maybe in a dragster. Yeah. You don't see this engine right here doesn't even have an inch crank. So we're dealing with tremendous load. That means this is like a shotgun. You shoot it, it's going to rip around like you would not believe.
Now, speaking to that issue, now I fully understand why you selected the engine you did. I mean, let's face it. You know, nobody who's doing these alternative energy experiments is made of money, and frankly, I have to congratulate you for taking this build as far as you have on the little bit of money that you've done. I mean, $2,000 into this build for what I'm looking at right now is outstanding. So I understand why you used the engine you did. Obviously, it was it was readily available, it was reasonably priced. You could incorporate it into the build. Your numbers said it would work, but if you had it to do from scratch, the way you think would be ideal, would you be looking for a stroker or something with diameter of piston? Would a long stroke serve this application better, or would a short stroke with a large diameter piston be better? What do you think?
Well, if you look at the concept, it could be multiple strokes. It could be in fact, on some of my designs, I actually had 4 pistons as a single stroke, like a compact compressor. The key is to actually get that compression that's needed to store into that chamber to be fired. Now, on this one particularly, it fits well because this piston's only 2.5 inches in diameter, which basically is about 4.9 cubic inches at a 1 inch stroke downward. So yeah, I got almost 5 cubic inches here, and when I take this shaft and put that 5, I can move it dramatically. So the pressure is very important, but also thermodynamics tells you heat is also very important. Now, my heat sink could be a problem when it's starting up, so I have to get that heat built up because, as Charles Laws says, when you have heat and cooling, you're going to have pressure and you're going to have vacuum. So you got to keep them at a typical temperature. This is why cars are usually running. In the old days, it used to be about 160. Now they're about 180, 190 because of the factor of the vacuum pulling in air from the intake. So the temperature is critical, but the beauty of it is that we're converting that temperature, that heat, into rotation of energy.
Okay, one question that's just come up in chat that's interesting. Do you have any idea what your design might do in terms of emissions? Have you thought about that at all?
That is a beautiful question. I want to tell you something about emissions that most people are unaware of. And I've been in mechanics. I worked for GM. I did mechanical. I know a lot about the emissions that a typical car uses. Is the emissions without the catalytic converter is the wasted fuel. The reason it's wasted, that valve on your port is opening up too soon. But on a typical IC engine, by the way, which is over 100 years old, 100-year-old engine, come on, we have to wake up. There has to be better out there. When that releases, it doesn't give it a chance to completely burn. This is where the ignition problem is truly the after effect. This is why we added the catalytic converter. The catalytic converter, believe it or not, people, your fuel is actually feeding that catalytic converter to keep it hot. In fact, most people think the fuel injection system is a beautiful thing when in fact it doesn't truly vaporize the fuel. If it did, why is the catalytic converter getting so hot as high as 800 degrees? Because that's also feeding that catalytic converter. The rotary is allowing that energy to be depleted completely, almost down to 0 psi when this comes around. That means that most of that energy is being burned inside the engine instead of being released by the exhaust valve.
It's interesting to consider. I do have an interesting comment out here. Somebody's asking if a pulse jet engine type concept might not be an interesting way to do your pre-combustion chamber. I don't, hey, interesting idea. I don't know. People are looking at this saying, some people are saying it's a little over their head. Some people are saying you need to turn the design over to the Germans that they could make it look pretty.
Well, the beauty of this engine right now, even though it's about 100 pounds, I estimate anywhere between 120 pounds, but believe it or not, my figures actually cut that in half, almost about 60 pounds. But let's look at this now. If I can get 150 horsepower out of 60 pounds, that's revolutionary in design. That means your engine in your car, instead of going to a mechanic, you can literally just change it like you're changing a battery. A battery will weigh more than this typical engine.
Interesting. Okay, guys, we are looking for questions from the audience. The chat's been moving kind of fast and furious, and a couple of really good ones might have got past me. So if you had a really, really, really good question for Tommy that got past me that did not get asked, please put it up there now. Okay, Tippy, this will be the working model. This is as far as he's gotten it. Tommy? That is a pretty good question. What is left to complete the build? Obviously, you're still working on the external combustion chamber component. What beyond that do you have to do before you can actually show us this puppy breathing fire?
Okay, what I've already done, I've actually pre-tested. I actually made engines that had a external combustion chamber to make sure the theory was correct. And it does show that when it expands and it actually sounds like a shotgun, and it does not move the piston that compress the air and fuel downward. In other words, it basically compresses it and shoots it forward. The typical thing right now that I'm working on, and I just got the mounting done not too long ago, a couple days ago, is to get everything synchronized in such a way. And basically all I got is the timing gear, which is basically no different than a regular cam in a typical small engine. When the timing belt actually turns the cam, you got to remember that pressure is very high. It's like releasing it. Think of it as a paintball gun. You got all that pressure and you pull that trigger and release it. That's what powers that paintball. Same thing that powers this. When that cam opens up that valve, it releases all that energy and diverts it into the rotary. And that's what it's basically basically I call it the bridge from the compression. It gets bridged to the combustion chamber, and then the combustion chamber is controlled by the timing belt, which releases the pressure.
Let's see, one question here. Can it run on hydrogen? I certainly don't see any reason why not. But would you like to address that one, Tommy? I mean,
Yeah, sure.
Do you think it would run better on hydrogen than any other engine?
Well, one thing about hydrogen, or I guess we want to more say HHO, because hydrogen, any engine can run off of hydrogen as long as you can control the oxygen. The HHO would be a different story because both of the mixtures are mixed together. You got 2 parts hydrogen, 1 part oxygen. You have no control of the burn rate. This is why it burns at roughly 4,400 meters per second. And the problem, it burns so quickly, it cools rapidly. This was what causes the vacuum or the implosion effect, we call it. Yeah. It could be actually converted into the rotary, but you would need a special valve system that allows it to push and then pull. And I do see the possibility of actually using HHO with a different kind of rotary model.
What other fuels might be applicable in a design like this? Inspirinator, of course, has a soft spot in his heart for veggie oil. You know, he's really enjoying running his diesel engines on veggie oil.
Well, the problem with diesel or anything higher than that, diesels is a different kind of fuel. Diesel works off the thermal heating of the piston stroke. Most people think diesel just, is squirted into the piston and then it compresses and goes boom, when in fact diesel is injected when the piston is at TDC. That's the hottest point, and then immediately explodes. But on this particular engine, the beauty of this, we're not using liquid gas. We're actually going to use vapor gas. And if you ever seen any of my prior examples of how vapors work, it's actually a much cleaner fuel because we don't throw the junk that the government is throwing in our gasoline. You ever notice why we don't smell gasoline anymore? Because it's not gasoline for real. It's too much chemicals that they cannot get rid of, so they put it in our gas tank so we can burn it. This is why the odor is so bad. I remember gasoline 10, 20 years ago, you can actually smell it 5 feet away. Today, you're smelling crap, and that's what they're giving us. They're not giving us a true gallon of gas. They're giving us a watered-down version of a low-cost fuel. When they add ethanol to our fuel, which is 10%, you're getting even less fuel out of that. So when we buy a gallon of gas, we're buying probably no greater than 3/4 of a real gallon of gas. The rest is junk.
So what I'm hearing you say is you're going to marry a number of the technologies that you've been playing with over the past few years. You do plan to use a vaporizer type carburation system on this unit to try and extract a little bit more efficiency out of it?
Well, the vapor, and I've experimented on vapor for a long time, and the vapor is the most cleanest way. When I start putting liquid fuel into this engine, I'll tell you what's going to happen. It's going to carbon up. The carbon is from all that crap that you're burning and all that liquid fuel you're not burning. So it's building up. This is why engines fail, because of carbon buildup. When you burn vapor, you're not taking the junk that they want to put in your engine. The junk is actually left over.
Tommy did bring up a good point. It's been pretty well known for about the last 25, 30 years that our petrochemical industry has a tremendous volume of highly toxic residuals from their production of various chemicals that used to be used all sorts of ways. You know, they used to put dioxin in with the paving stuff that they paved the roads with, and of course, you know, people started dying. We had Love's Canal. I don't know if many in the audience are old enough to remember that, but an entire community in New York was basically despoiled by chemical dumping sites there. So they had all this stuff, but they didn't know what the heck to do with it, to get rid of it. Well, for about the last 25, 30 years, they've been mixing it into our gasoline, and you get to pay to put a chemical processor on your automobile called a catalytic converter, which was specifically designed to burn this stuff. So you get to pay to get rid of the crap that the petrochemical industry creates as a byproduct. And that's what your catalytic converter is doing. It's getting rid of their chemical crap that they can't find any other way to get rid of.
That's absolutely right. You hit it right on the money. If people only knew the crap they put in our gas, there is over 100 chemicals in our gasoline today. And what are these chemicals? Chemicals they cannot get rid of, but they can burn it in your system. The reason they can burn it in your car is because the catalyst that is over 800 degrees, people, where do you think they get that heat from? From your fuel that you buy. In other words, your fuel is not going directly to your engine. It's feeding a catalyst to burn this crap that they're putting in our gasoline.
All right, guys, we have run just a little bit beyond 10 o'clock, so I'm starting to think you know, seriously about letting Tommy go. He's been very kind. He's given us you know, all the time he promised to give us. But if there are a couple of more really good questions, now let's not have any bullshit questions. I'd like to hear a couple of really good questions to close Tommy's portion of the show out with. You might have asked a good one that got past me. You're just going to have to forgive me. I don't read that fast when the darn chat's going as fast as it has. Somebody mentioning alcohol. Can it burn alcohol? Can you comment on that?
Oh yeah, alcohol is no different than dragsters. I mean, but you have certain kind of percentage. You know, you can burn 90% alcohol, but remember that 90% is only 90% alcohol. The 110 is actually water. So you have to actually vaporize that to pull the alcohol out. Unlike anything else.
Kane's asking, what about the stroke in between? You've got an intake stroke where you're sucking the mix in. You've got a compression stroke where you're compressing it. What are you going to do with the exhaust stroke?
Okay, think of this, these two valves, they don't function in the engine. In other words, these do not function. We put a head over it. These just sit there, basically doing nothing. In other words, the cam is being taken out to do that. So basically, we're just using this to pull a vacuum, compress the fuel and air mixture, diverts it over.
Okay. So the valves are basically disabled. They're just plugging the holes.
They're useless to what I need it for. I just need to compress the air and fuel mixture. I don't want to use this stuff. In other words, if I use the valve, then it's a 4-stroke. But if I use it as a compressor, it's a 2-stroke.
I see. So as far as, you know, everybody who's thinking in terms of this being a 4-stroke engine, a rough comparison would be sucker goes off on both the compression and the exhaust stroke, right?
Right. In other words, when this turns
Okay.
over, when this engine
Okay.
actually turns over, give you an example, it's compressed now. When this turns over, it turns this down and then actually pulls in air again to recompress and basically just keeps firing it at every revolution. This is also
I
very
got it. So
important.
so what you got, you this external combustion chamber has a check valve on it. I assume you've also got a similar check valve arrangement to your vapor carburation system. So when it's going down and it's sucking, it sucks off the vapor carburetor. When it starts to compress, the
Right.
vapor carburetor closes off, and
That's right.
the check valve going to your external combustion chamber. And yes, in Spirinator, the spark plug goes on the external combustion
Yes, it
chamber.
does. Yes, that will actually be over in this area, the combustion chamber. I'll probably have to make this longer. And the beauty of it, here's why I did this engine. It would probably cost me $2,000 to build a proper compressor.
Oh, if you could do
So
it for
I'm
that.
working with what it is.
Yeah, you took something off the shelf that would do the job, and you saved yourself thousands of dollars in development, not to mention the time. So you get your prototype out there where it can be seen faster and for much less money. I admire this build very much. Zero Fossil Fuel has mirrored that compliment. He really admires your build. Let's
Thank you.
see. That makes sense to me. Okay, I think the light bulbs are starting to go off on a couple people's head. I think our explanation of the check valves and how fuel actually. Everybody was looking at those valves, saying, "Okay, I think we're
Right,
starting to
because
get it
because
now."
what it looks like, if you just do that, you might as well just make a pump, for God's sake.
Now
This is not a
Tippy's
pump.
got a good one now. He's holding you to task, and I see the same fatal flaw in this design. Now you've got this little tiny combustion chamber in your rotor, but you've got this huge area of the disc. How are you going to seal that? I would think that there'd be a good bit of compression loss. I mean, if your seal is too tight on the rotor, you're not going to get free motion. If it's too loose, you're going to lose compression. So that's a real fine line you're going to have to draw there, isn't it?
That is absolutely right. This is why the efficiency of this rotary is going to depend on how well the vane and the rotor itself is sealed. So this is why I have a basic rule. 75% of it is being converted and 25 would be through leak. Now we're dealing with a we're doing anywhere between 2 to 3 thousandths of an inch difference. But you got to remember, this pressure isn't going in slow. This is tremendous high speed when this is released. Like a gun, for goodness sake. It won't have time to leak. It's going to do some motion.
And what are you going to do about lubrication? I mean, I assume that rotor's got to be lubricated. Is it going to be in like an oil bath, or are you going to inject oil on it? How are you going to keep it lubricated?
Actually, this particular design does not need oil. And the reason it does not need oil, the rotor is finely cut where it gives me, in other words, I can spin the rotor without any friction against the walls, but it only has about 5 thousandths of an inch away from that wall. Now, I gotta, of course, the thermal heating could be a problem, but it'll take a lot to heat up this heavy duty engine. But the unique thing, the vane itself also is very tight. So when this is, the vane is actually made of a metal that does not need lubrication, like brass or bronze or
Okay.
oil brass vane. So the vane itself does not need oil, just like
Okay,
a brass
Hillbilly,
bearing does not need oil.
Hillbilly's playing Tommy Reed out there tonight. He's going to be the dissenting opinion. He says, "Yeah, it's pretty damn cool, but where the hell's the hard data?" And I would say to Hillbilly what I normally say to Tommy Reed: we are looking at a pre-production prototype. We're hoping that sometime real soon we get another visit from Tommy Reed where he shows us this sucker breathing some fire, at which time we hope he will be collecting the hard data. You're justified in asking the question, but it's a little premature at this point, Hillbilly. You just got the same speech I quite often give this fella Tommy Reed that we all know and love.
Absolutely. But we're looking at the heat. People don't understand what's going to happen is that heat's going to rapidly cool when it starts to expand. It's only when an engine is under a load, but you got to remember we're dealing with tremendous torque unlike any engine out there. Show me one engine at TDC that can convert that into instant torque. You won't find it. The rotary does that.
Okay, I've got two more issues that I'd like you to address, Tommy, and then I am going to go ahead and cut
Sure.
you loose. We are running, a good bit overtime. You've been very, very patient to put up with us as long as you have. But one question that's come up, and I think it's certainly relevant with this design, what about the shaft? Or how are you sealing that shaft? There's a number of people in the chat room that see the shaft as a potential for compression loss. That's one item I'd like you to cover. The other item is, oh, damn it, I lost the question. Where'd it go? Darn it. I had two good questions lined up there. Please address the shaft issue while I try to find this other one out here.
Sure, absolutely. I have done pre-testing at 120 psi where when this is actually moving, the amount of leakage, we're talking a very slow, little amount of leaking. You got to remember how this is actually designed. If you look at that graphic image that Scarecrow showed earlier, you've seen that the exhaust port is on this side. So whatever leakage there is, it's going to go to the exhaust port. In other words, it'll never get to the bearing area, which is already pre-sealed. In other words, when you put something in here, it may try to bypass a little bit, but it's going to come from the exhaust immediately. But the key is that at the proper timing, when this is released, I don't know if you know anything about PSI, but take a scuba tank and release some of that pressure and you see what kind of energy comes out. It won't have enough time to leak completely out. It's going to turn the rotor, as all the prior tests showed. Look at the old Scarecrow show from the small rotary when there was a tremendous amount of air leakage and it actually turned the generator to generate electricity. Remember that, Gary?
Oh, yeah. Yeah. Well, now, I tell you, I know there was another good question out there, but it got past me. I'll blame it on old timers disease. And we have gone a good bit over time, and I do need to start thinking about shutting things down here. But as is the custom, before I cut you loose for the evening, Tommy Reed, I would like you to have the floor to make any parting remarks or comments that you might have. And I share the sentiments of many in the audience. Yes, there are the resident skeptics. God bless them. We need every one of you. But good luck, Tommy Reed. We really look forward to seeing this puppy burning fire as soon as you can show it to us, man. There's a lot of people out there just salivating to see this thing breathe fire. Now, I give the show back to you for any final comments or statements you'd like to make before I cut you loose. Please, take it away.
Yes, on this particular design, always remember a theory is only a theory, but you got to make the thing become reality. What I'm trying to explain to you, I've done all the prior testing. I've shown that the rotary can run under pressure. I've also shown that you could build an external combustion chamber that actually functions. The key is real data is correct. You have to put it under a load. But I could tell you this right now without a doubt in my mind, this thing will breathe fire. How well will it breathe fire? It depends on the amount of seal that could be done on this engine. To say this won't run is like saying you can't jump out of an airplane with a parachute. You're going to die. You're gonna fall to the ground very slowly with a parachute. This is well designed. I have put a lot of time and effort on this design to make sure it does work. So far as not running, it doesn't happen. It will run. Everything I've ever built always worked. The efficiency is when you actually tune it. That's where the key is. But to say it's going to be more than 3.5 horsepower, absolutely. And here's the key. It's going to use the same amount of energy that 3 horsepower did. And that's my conclusion for tonight.
One more little aggravation before I cut you loose. I'm looking at my schedule here. How about sometime in February or March to see that? Can we get you back February or March?
That's where my project should end. Right now, I'm working on the finding parts. That's another thing, trying to find on-the-shelf parts. But everything from the head and down into the combustion chamber is going to have to be properly machined, and that's where I'm looking. Hopefully, within 2 to 3 months, I should have it breathing fire.
All right. Well, I have penciled in a couple of dates with Tommy Reed's name on them in late February, early March, and I'm hoping to get a note from you saying you're ready. Because I'll tell you what, I definitely want to see that thing burn fire. Tommy Reed, thank you so much for a great presentation.
Thank you. Thank you.
It's really been a pleasure. You have a good evening, sir.
You too.